Greetings to everybody. Nice to see all of you here. I'm Michael, and today with my colleague Simon, we will tell you a little bit about the new Kotlin compiler, called K2.
Feel free to ask your questions in YouTube chat. We will read the most interesting ones during the translation, and then there will be a space for all the questions that you will ask.
The recording of this talk will be available directly after the translation ends. Okay, let's go.
Let's go.
So, today we will talk about the K2 compiler. Moment. About the agenda. First, we will talk a little bit about why have we decided to rewrite the compiler. Then we will go top-down, beginning with high-level compiler structure, the front end and the back end. Then we will consider K2 frontend more attentively as a transparent box. Then we will tell you a little bit more about the most complex front-end component, the analyzer. Then we will move to the name resolution. It's the most complex task of the analyzer. And finally, during the conclusion, we will tell you a little bit about the performance. Okay, so why have we decided to rewrite the compiler? Now we are 10 years old. The language has evolved. It includes some number of legacy features. This means that compiler have to support them and have to have some legacy code inside, some legacy data structures inside. So the code is dirty. Also, the first version of the Kotlin compiler, the main goal we had at that moment is to enable fast development, to develop the compiler as fast as possible. The compiler performance was also a goal, but it was a secondary goal. Maybe that's why compiler is not so fast as we wish to see it. Also, rewriting the compiler allows us to get better memory locality, to enable multi-threading, which is very problematic with the compiler 1.0. To have cleaner compiler structure, which is very important for developing compiler plugins or IDE plugins. To have better multi-platform support. The problem here is the multi-platform appeared later than the first compiler was developed, so it is not architecturally supported and it exists a little bit aside. Also, the K2 makes for us easier support for some language features. For example, some features can be supported directly at desugaring stage at the beginning of the compiler work. We will talk about it a little bit later. Okay. On the top of a mountain, we have the compiler as a black box. It has some inputs, source code, dependency modules, flags and settings, and some outputs which depend on a backend used. For example, it can be JVM bytecode. Now, one more level down. In high-level compiler structure, we have front-end and back-end. The main task of a front-end is to determine the program semantics. The main task of a backend is to generate output, for example, JVM bytecode. Also, backend performs such tasks as optimize performance of a program, make some code transformation, and so on. About the program semantics, what is it? Let's consider a simple example. Here you can see function hello, which calls println. What semantics can be extracted? Well, first, the function is public because it's default visibility in Kotlin. Second, the user value parameter has a type of Kotlin string. The return type of hello function is inferred to Kotlin unit. The function exists in example package. This can be taken from a package directive. After body analysis, we will know even more. For example, the user component of a string template here refers to user value parameter of hello function, and it has type of Kotlin string. The whole string template also has type of Kotlin string, and println call in fact refers function from Kotlin IO package which accepts string and returns Kotlin unit. The talk of K2 is mostly about a front end, so let's consider our front end in more details as a transparent box. At the beginning, we have source code. Then parser runs and generates parse tree. What is parse tree? In Kotlin compiler, we use the structure from IDEA platform here. It's program structure interface, or just PSI, and it's a concrete syntax tree. The word concrete means here that we do not drop any information while building the syntax tree. For example, we keep all comments, we keep all parentheses, so on. The top level node for a function is a function node. Then for its body, we have call expression node. Some levels lower, we have a string template node, and even lower, we have reference expression node for the user component. After parse tree is built, we should build front-end intermediate representation, not just front-end IR. This work is performed by raw front-end IR builder. And what is front-end intermediate representation? It's also a tree. Moreover, it's a syntax tree, but an abstract syntax tree. The word abstract means here that we do drop some unnecessary information. For example, comments, for example, parentheses, for example, funky word here, because we no more require it, and so on. However, the top level node here is more or less the same. It's simple function. Some information is added into front-end IR. For example, type references. The string type reference exists in source code, and it's represented by user type reference. However, the return type of hello function does not exist in source code. It's implicit, and it's represented by implicit type reference node. For a function body, we have a moment when we have resolved type reference from the beginning, because we raw builder knows that string template type is always Kotlin string. Also, Frontend IR includes so-called simple named references, which are later resolved. Here we have two of them: the explicit user named reference for a string template component and implicit to string call, because each string template component should be converted into string. This toString call is an example of desugaring, which is performed by raw frontend IR builder. Desugaring simplifies code, but not in terms of human understanding. It simplifies code in terms of compiler analyzing. For example, all if expressions are converted to when expressions for universalization. For loops are converted to while loops with explicit iterator. All destructuring declarations are destructured. All square brackets are converted to get or set calls depending on the context. Some parentheses are converted to invoke calls in case frontend IR builder can determine that nothing more is possible here. After frontend IR is built, analyzer runs. This component modifies frontend IR by adding some semantic information. Some examples. Here we have some type references resolved. All type references should be resolved during analysis. For example, value parameter type is resolved to Kotlin string. Function return type is also inferred to Kotlin string. For a function body, we have some other examples. For example, constant expression hello, comma, which is a part of string template, also has a type of string. User named reference is resolved to value parameter. After analyzer finishes and semantics is extracted, so-called checkers are run. Checkers check frontend IR for errors or warnings, and if necessary, they generate some diagnostics. Only after checkers finish their work, backend can run. Because otherwise, if backend is run on erroneous code, it can finish with some exceptions or so. Okay, now I will repeat from the beginning. First, we have source code, then parser runs, it builds parse tree, then frontend IR builder converts it to frontend IR, and then analyzer adds semantic information, and then checkers generate diagnostics, if any. The analyzer is the most complex component here, so let's go one more level down and consider what it does. Analyzer consists of some stages. You can see these stages on the slide, and the first of them is import resolution. During import resolution, we should process imports. Usually we have some imports like this one, ABC foo, and usually it means that somewhere else we have package ABC and function foo inside this package. However, in fact, import resolution drops the last part of import and resolves only the remainder. There is a reason for it. I will tell about it a bit later. The same thing is true for star imports. We resolve only ABC without taking star into account. So how import resolution works? We have ABC. First, we suggest that it's package ABC. If there is no such package, then we try to suggest that there is package AB with an object C inside. It's also possible, and so on. So to answer my own question, why we do not resolve the last part of import. Here we could resolve it because we have object C with with a function foo inside. However, here we can't because object C has no function foo inside, but it's inside base class. However, to understand it, we should first resolve supertypes and its performance during the next stage. And to have import resolution universal, we do not execute last component resolve here. The next analyzer stage is type resolution. In turn, it consists in signature type resolution. Here we resolve types of value parameters, of function return types, function receiver types, and the separate stage of supertype resolution, which is performed first. Also, type resolution is the first stage when the tower goes into the action. What is the tower and why do we need it? So you can see the tower here. And when we resolve some name, no matter is it type name or function name, we should search for it in different name scopes. Each class contains some names. Super types of class also contain some names. Some names are imported, like another B in this example. Some names are contained in the same package. Some names are imported by default, like string here. Some names are imported by star imports, like lib.star here. How the tower works. When we want to resolve some name, we start from the lowest level of the tower. At this level, we search for this particular name, and if we find exactly one candidate with this name, then the resolve is successful. If we find no candidates, then we should go one level up. If we find two more candidates, it's ambiguity, so an error. Now let's consider type resolution stages a bit more attentively. About supertype resolution. This stage is specific because it can perform so-called jumps from one file to another. Let's consider an example. Here we want to resolve base nested name. It's a supertype of nested class. First, we search for this name inside class scope, inside top level class, but there is no this name inside. So we must go to supertypes, and supertype here is middle. It's defined in another file, so we perform jump to middle KT. Middle class also does not contain base nested names, so we go to its supertype, its base. It's also defined in another file, so another jump to base KT. And finally, base class contains base nested name inside. So success, we have found it. The next stage is signature types resolution. It's easier, and here you can see an example of tower usage. In this example, we wish to resolve four types: A, B, C, and string. We have a tower. And the first type, A, exists at the lowest level, simple imports. We have import another A, and A is taken from package another. Then we go to the original package to resolve B type. It exists in the same package, which is called up, so it's here. Then the C type, it can be resolved at star imports level. We have import lib.star, and C class exists in package lib. Finally, the string type, it's not imported explicitly, but it's imported implicitly. Kotlin package is the package which is imported by default by each Kotlin file, so string class is taken from there. Okay, and now about body analysis. Simon.
Hello again. I'm Simon, and I will tell you about next part. But first, let's review some of the questions you asked. First question was, is there any possibility of doing something like val list equal to collection literal, I guess. So speaking about collection literals will be possible to implement once we will get the right design, because the main problem with collection literals is actually how resolve should work for it. Like, do we want them to be tied to some particular list implementation, or do we want to allow users to provide the implementation for underlying collection of the collection literal? So it's the main design point that needs to be solved before adding collection literals to the language. But of course, new frontend allows us to implement that, and potentially it will be possible once we get the right design on that. Also, next question was, so after a new frontend, Kotlin syntax will improve even more. Yes, it will improve, and we already have some improvements in frontend in K2 compiler implemented. Those improvements, for example, include better smart casting capabilities. So now we can smart cast to the type that we not that we will not be able to smart cast in the current compiler yet. Also, there is some language features that is in prototype stage for now. I guess there was the third question. Are we in the same room? Well, actually not. We in the two rooms that are next to each other. But it is a different tree on background. I see one more question. Two more questions here. About name resolution, let's talk after the part about the name resolution. Any plans for pattern matching in Vans, where one can branch on property values, etc. So first of all, we are trying to get this design done for pattern matching, but it's not like in early discussions. But we are already planning some deprecations that will probably allow us to implement that. There is a it is in design, so I think some of the time we will get a pattern matching, maybe. So let's go to the next part of the talk. So body analysis. What does body analysis do? Well, body analysis is the analysis part that's responsible for analyzing all bodies. It is including property initializers, including bodies of the functions. It's including anonymous initializers within classes, everything where expressions can be found. So it is just a top-down pass over our code, one block at a time. And it's split in two parts, actually. In first pass, we analyze declarations that have implicit return type, which is not specified explicitly. Here, for example, function greet have not specified its return type. So here, to analyze this function, we have to analyze its content to infer its type. But we have another problem here. We have a function hello, which type also not specified in here. So we need to perform jump to file where the hello is defined and infer type for it. Here is the type for string literal can be inferred because we know that every string literal have a type of string. So we infer it, then we infer and store the type of the hello function, and then we can write out the types for call to the hello function. Then we can finally found the type for greet function. So it's the main reason why we first analyze implicitly typed declarations, because it can also perform jumps during the analysis. Actually, it even can lead to the some impossibilities to analyze. For example, here to infer a type for function foo, we need to infer the type for bar, and to infer type for bar, we need to infer type for foo. So it is recursive, and that's it. But if you specify a type explicitly here, then we will start by analyzing bar function. Then we already see that the type for foo function is int, and we can infer the type for bar function that it is an int. So after that, after all implicitly typed declarations analyzed, we can analyze all the explicitly typed declarations. Why? Because its bodies does not depend on bodies of other functions. So for example, here we want to analyze this call. As we already know the type for greet function, we do not need to analyze body of greet function, so no jumps here. And as the type for send function is typed out right here, we can just not analyze its body and already analyze the body for function send greeting. And it means that all of those functions can be analyzed independently, opening possibility for multi-threaded analysis. Because body analysis is one of the longest parts of the whole body of the whole compiler runtime. It will allow us to improve performance even more. So one of the most significant parts of the body analysis is the name resolution. So yeah, there was a question. Name resolution here is for runtime or for compile time resolution. In Kotlin, there is no runtime name resolution because Kotlin is a statically compiled language, and we really have all the fully qualified names in the bytecode or in the native code. So there is no runtime name resolution performed, and the topic on name resolution will be about the compile time name resolution. So what's a name resolution? Name resolution is main part of this process is binding particular names found in code with its declarations. Here you see that username refers to the username parameter of the function hello. So let's see how it's being performed. It actually consists of different stages. And let's see what those stages are. Those stages are actually tower resolver, applicability checker, and overload resolver. So what first tower resolver does in this scheme? It provides candidates. Let's see what the candidates here. So let's consider it's a call for function hello in this highly complicated program. Here, all the possible candidates for this function that could be found from this actual position. So first, as we found those candidates, we pass that to applicability check. Applicability check checks, for example, visibility, parameter count, and parameter types, receiver types, and all of that stuff that really selects on how is this candidate matching for our particular call or not. So here, as you might see, we have 4 candidates that are not matching because its types are not string and cannot be string. And there is 2 candidates that are matching because string is a matching type of the literal, and char sequence is a super type of string, so it also matches. Once we checked those candidates, we drop out non-applicable ones and keep those applicable. Then we pass them to overload resolver. The goal of overload resolver is to select best candidate if it is possible. If not possible, then it will report ambiguity because it cannot determine which candidate is better. So how it does that? Actually, char sequence is a super type of the string. So we tend to select more precise candidate. Like, for example, you have a function that takes number and function that takes int. We'll select one with int, not a number class. And same for char sequence, which is super type for string. So after all of that, we selected one candidate for function hello was a string parameter, and now we got the result. So that's it. Most complicated part of the name resolution is actually a tower resolver, because it have to find candidates in some really strange combinations that we might have in Kotlin. Let's take a look. So, and as in the situation with type, we also have a tower, and we process this tower from the bottom to up, and search in the scopes for declarations that will match. Like here, we check for hello, check for its parameter it's not matching, also checking this hello in other local scope, then checking an extension receiver of this whole declaration. It also have function hello that is not matching, and so on. So then we finally check origin package example, as you might see, and at the end we check the star imports. But really, this tower is having something like imports on the top, same as for types. There is also a special case for explicit receiver. For explicit receiver, we have to consider the scope of the type that is in our receiver. So let's see, here we trying to resolve that name hello, and we have to consider scope of its receiver. So it's typed world, as you might see, and then we look into the scope for this class first. Other levels are considered if there is no match found in the explicit receiver level. One of the most complicated examples in the tower resolver is the invoke operator resolution. In Kotlin, actually, each call foo braces some arguments might mean foo.invoke with those arguments, because we have a invoke operator convention. And let's see how this is resolved. So first of all, let's consider this example. Here we have a call to function foo with argument of string. And in first, we start a search for really function foo with arguments. So firstly, we try this function, but it's not matching because its number of arguments is different. Then we also check those locals for property, which is named foo, but there is none. So let's proceed. Then we go to the class level. There is no function, but there is a property. And then all the magic happens. So we found that there is a property called foo, and now we have to consider if there is a invoke declared on the type of this property, which is indeed foo here. So first, we should consider it as an explicit receiver. So here we have a invoke which is not matching by the type of the argument. So we're analyzing this expression right now. And then we proceed from the bottom. And like we go up, up, up. Then all the search tasks are synchronized. And then they are going upwards, finally to find a invoke function that is matching. So interesting fact is that all of those search is implemented as a coroutines. Really, all of those circles here means a different search tasks that are started and synchronized once it's entered one of the level of those tower. So each of that are separate coroutines that are started once, for example, those two black and white searches are started once we start for looking for this call shape, and then orange one is started once we found a matching property. So that's it. So let's go to the conclusion now. So we just discussed how name resolution works. So let's take a bit more.
Okay, let's continue. I see some questions and comments. I think it's better to answer them first. The question about duplicating the logic inside IDE. No, the logic isn't duplicated. IDE reuses frontend. It reused the old frontend, the current frontend, and it will reuse the new K2 frontend. So what else? Is it okay to expect improvements in generic type with new compiler frontend? We have to use RiFight and inline fun to know type of type parameter and so on. In this aspect, I'm afraid that no, the types are the type parameters are erased. The generic types are erased inside JVM. So at this moment, I don't understand how we can implement it in new frontend. Then another interesting question. I think not yet. So, okay, then let's go to the conclusion. And I would like to say a few words about front-end differences and performance differences. About the current front-end. The first major difference is the active use of PSI during all stages inside current frontend. In contrast, the K2 frontend uses PSI only for conversion to frontend IR. Also, the next difference is that the current frontend stores all information in gigantic structure, so-called binding context, which is a huge collection of maps. K2 frontend, in contrast, stores all information inside the frontend IR tree itself. Here you can see the difference between PSI and frontend IR. You can see here that frontend IR is lightweight, relatively lightweight, and PSI is relatively heavyweight. So frontend IR works faster. Also, here you can see the difference when we are trying to understand to which point some access like user here is resolved. You can see that current frontend should access two maps from a binding context, this one and this one, and the K2 frontend just accesses a tree node member. It's also faster. Then the stages with jumps. As was said before, the K2 frontend contains only two stages with jumps. There are super type resolution and there are implicitly typed declarations part of body analysis. In contrast, the current frontend can use jumps at almost any stage, which provides worse locality, and it means that the current frontend also slower here. To summarize, why is the current frontend slow? PSI active use, binding context, large maps, and lots of jumps during resolution. In contrast, the K2 frontend uses frontend AR, which is more lightweight, 3 accesses, and jumps are limited there. Also, K2 frontend includes some more or less minor algorithmic differences. For example, here we are trying to resolve plus function call, and the current frontend here takes the plus candidate from the tower, and then later it rejects it during applicability checks. And finally, it reports on receiver. The K2 frontend reports unresolved reference immediately. In this case, it drops the plus candidate from the tower immediately at the moment it understands that the receiver is wrong. In fact, standard library contains a lot of plus functions, so the resolve of plus really takes a lot of time in a common program, so it's more or less important. From our measurements, it saves us about 3 or 5% of front-end working time. Also, the last but not the least, the K2 front-end development procedure includes daily performance control. Each working day at the morning, I open the chart like this one. Here you can see the build times of IntelliJ community projects by K2 on 4 different build numbers, 4 different time moments, in fact. So here you can see some step up. It means that performance became worse at this point, and it's a signal for us that we should perform some analysis, which commits have broken the performance, how they can be fixed, can they be fixed, and at last we can see the step down. It means that we improved something in the commits which provoked the performance loss here. And finally, some measurements. First, K2 is front-end, so measurements for front-end only. Here you can see that for different projects, the new front-end is about 3 times faster than the old one. However, the front-end only measurements aren't very important because, in fact, almost nobody runs front-end only. So let's consider front-end and back-end together. Backend wasn't optimized during K2 project, so we have worse coefficients. Here you can see that for different projects we have coefficients around 2. So K2 compiler is about 2 times faster than the old compiler. And the last word from Simon about Gradle.
So speaking about much bit material use cases, in reality, you have build system, and really build system also responsible for your build times. And let's see how. Here is a dump from some clean build of a Kotlin project taken on my PC. So here, from it, you can see then that the Gradle task takes 282 seconds and running of compiler approximately 230. So it's only 81% of the time. So remaining time is wasted within the build system. So build system might affect the overall build performance as well, because there is some tasks that should be done, and for example, some progar to run, and this also affects the overall experience, of course. But here we developing compiler, so we trying to optimize a thing which takes most of the time, but yet not to think about build system is strange. Also, in the situations of incremental recompilation, build system can take much more percent of time because compiler running particularly for small time in the incremental builds, because in the incremental build compiler is incremental, so it have to recompile only a few classes, and build system can take up to whole the time the build runs, because it have to check is everything is up to date. It have to run the tasks that are not so intellectual to detect should it be recompiled or not, and so on. So but in first place, cleaner K2 allows us to have cleaner compiler structure that simplifies us to introduce new language features, because now we have desugarings that helps a lot, because we can really drop some syntactic sugar on the time of the building front end IR in the front end. It makes things faster, and it also opens possibility to implement multi-threaded modes within the single module for compiler. So it also will improve performance in case when you have one big module with a lot of dependencies and a lot of code, and do not want to split this module really. And this will also help, and we have some prototypes on that, but not yet. We're still working on those. So thank you, and let's read the questions. So let's see what questions I see in our document. I guess the question about sharing analyzing logic is already answered by Mikael. And about generic types also. So I see one question from either any improvement in the type inference. Really, K2 reuses new inference that was introduced some time ago in the current Kotlin compiler. So so at least it will be not worse. And also there is a new smart casting engine that allows you to have more smart casts, and it might count as a improvement in the type inference, because it's some kind of multi-statement type inference also. Mikael, do you want some questions to be addressed?
Yes. Question about linting tools. Linting tools like KT-lint be able to use the new front-end constructs. Well, we hope so. I think that the compiler plugin infrastructure, which will be provided as preview together with K2 preview, it will allow to write well, additional checkers and report additional diagnostics. As I know, it's the exact thing Kotlin does. Simon, do you have something to add here?
Well, I have something to add here, yes, because we're also working on some API that really encapsulates the front end and allows you to run like the ID mode of the front end, and it's needed for Kotlin symbol processing, for example, and will be also used by ID, of course. And but probably if you want to run some maybe code generators that generates code based on what you have within your project, or maybe some linting tools, it can be also used there. I see also the question, where do optimizations done for newer JVMs lie in the K2? How K2 affects ease of delivering those optimizations? So optimizations is a part of backend, mostly because JVM is just one of our targets that we compile into. And code optimizations, I mean the output code optimizations is done there. But I'm not aware about some of the new features in the JVM that really allows you to optimize something. Probably maybe something about atomics, but there is not a lot of the things that allows you to optimize code better. I also seen a discussion about Java evaluation extension proposal 305, which is pattern matching for instance of. And really, speaking about this proposal, is the thing that Kotlin already have. You can check for object, if object is an instance of some particular class, and have a smart cast on that. So actually, it's not a pattern matching, at least in the way it presented within the document that I can Google in one action. So actually, it's more about the smart cast that we have in Kotlin, because you can check, you can have a check for instance of string and then call length directly without need to assign a new variable name, for example. So that's the power of smart casts. There is also the question, did you already prepare it for introduction of contextual parameters? Okay.
Yes. So we usually call this feature context receivers, and it's in progress. Hopefully you will see it in Kotlin 1.7, and probably you will see some first version of them in old frontend, and probably enhanced version of them in new frontend a bit later. Have you something to add?
I see more questions, really. So there is more question. Does K2 bring any changes to human-readable bytecode in IntelliJ IDEA? Well, it might bring some changes to changes in behavior of the front end, but this action will still work once we have K2, and well, it shouldn't change a lot because we are trying to match basically. And also there is a question about things like Loom. As I remember, Loom is more of well, it's more about APIs, so it's encapsulated within. So you don't need a special compiler support for Loom, because Loom is more about the JVM itself. And I think so. Once Loom will release, we will see if there is something that compiler could help you with. So also there was some, yeah.
Can I add something? It's
Yeah.
about a question about show Kotlin bytecode. So I can add here that we have a set of tests in compiler directly about the bytecode, and these tests check that bytecode in the current frontend and bytecode produced with the help of the current frontend and bytecode produced with the help of the K2 is matched. And at this moment, most of these tests are passing. So we can hope that bytecode is the same, and it's more or less important because sometimes with a different bytecode we can have, for example, less optimizations work in JVM itself. So we try to keep it as is. So somebody asked about our office. Yes, this office is located in St. Petersburg. Something else?
Yes, there is a kind of lifestyle question from Smith, I guess. Overall process of creating new compiler named SK2. How complicated it was, and did you guys enjoy it? Hope it was. Love Kotlin. Thank you. So I think we can answer on that both. So your experience
is it was great experience. So really, I would say that the real birthday of the new frontend is January 2019. We have done some work before, but it was a small work. So now this project is run for almost 3 years, and it's almost finished. I think we will require something like a year to have it release it or close to release it. But hopefully soon you will see a preview, sooner than in a year. And it's probably for me it was the best work at JetBrains.
So speaking about that, it was really interesting experience because like literally I and Mikhail was starting that project those 3 years ago, and we pair programmed some of the like root parts, some of the root parts of the type resolve, import resolve that we talked today, and I'm still finding those code and like remembering those good old days without all those complications that came for now, because like literally for now we have to fix all the issues, make projects compile, and really it is hard to match everything. It's hard to fix bugs within like type inference, within analysis order, and all this stuff that we have to match precisely to make the new frontend work in the like for the code that everyone have here in Kotlin already. So, but we already can compile our Kotlin project. So, and literally we using K2 compiler for our everyday work. So it's enabled for our team. So that's how it's going. I see one more question here. It's about dropping old Java versions like 8. I would say I do not remember any plans like that, but something might change. Anyway, we will hear about it in deprecations and our blog posts. So stay tuned on that. And also stay tuned on preview of the K2 compiler. I guess.
Mm-hmm. I also do not expect that we drop Java 8 in the nearest future. So at this moment, you can keep you can feel yourself safe. The new question: is there any syntax changes with K2? Well, you can expect some new syntax introduced. There is, as I remember now, no syntax dropped. Am I right, Simon?
Well, we're deprecating some strange language constructs, which is unobvious, and it will be deprecated beforehand. So at the point when K2 compiler will come to release, you will already receive all the deprecations for it. And we consider all those deprecations that really no one should have code like that. It's just literally very, very, very strange corner cases that we have in Kotlin, and very strange behavior. So I guess let's answer the latest question and finish on that. So those shorts are Kotlin swags. Is it possible to win Kotlin swags? So those are presents for 10 years of Kotlin that we have for our team. So I'm not sure that it is possible to get it from somewhere, but you can print it for, I guess. So thank you everybody for all your support and for listening to us today. Have a great time of the day, I guess.
Mm-hmm.
Thank
Thank you. It
Goodbye.
was much glory to meet all of you. Thank you.